1 and 2?
Yeah. And it's gonna be our hardest stretch. So
You just have
hope trying to think of how good. Yeah.
Are you playing or are you spamming your friend? Are you playing?
I'm spamming my friend. But it's a constant thing. It's very annoying. And I type weird. I type with one thumb and one finger like this.
Okay.
Isn't it weird how sometimes we will type with just one thumb and other times it's like two?
Okay, what?
Like sometimes I'll just be typing with one thumb, like in my one hand, but then you go with two hands.
I type with just a couple of fingers.
I do it. I type with like, I'll use like two fingers for the most part, but I'll use like a couple fingers for certain keys.
Yeah, I just do a couple of fingers. My wife drives my wife nuts. It's like, how is possible you can write a dissertation with just a couple of fingers? And she's like looking around and typing, and like,
I can do that on my phone, but I can't do it on a laptop. I ain't look away from the screen.
I don't look away from the screen and type. I just won't be staring at what I'm typing. I don't want to type.
okay, so we're gonna continue. We're gonna finish the plan that we're working on Monday, and then we're gonna do another one involving 2 dimensions. Okay, so the one we have kind of like a wedge, something like this. So from here to here is 1 meter. This angle is 45 degrees. I think, and we have a delta B of 50 volts. Okay, what else? Oh yeah, the gap here is 4 millimeters.
That's like 5 millimeters into the 5 meters into the page.
And 5 meters into the page, so this is a 1 times 5, 1 by 5 meter plate. And we also know that there's a dielectric. And this dielectric has a relative permittivity of 1.5. Okay. Now, the key issue here is that we have an interface of a metal with a dielectric. Okay. So here there's going to be a charge, there's going to be an induced charge, but we need to be careful because this is a charge that, well, we have a boundary between a metal and a dielectric. So remember, we talked about this long time ago. So this is one example of when it's been applied. So from a previous example, we calculated the electric potential, and the electric potential was going to have this shape. Okay. And then looking at the boundary conditions, we found that the electric potential is going to be V naught of phi naught. So that's going to be the electric potential. And from this, we know that the electric field is going to be minus rho v, and in this particular case, it's going to be minus v naught rho phi naught phi hat. Okay, this is basically what we did last class. So okay, and remember what we want to find out is what is the charge. We want to find out what is Q. that we have in this on this configuration. And when you have an interface of a metal with a dielectric, okay, remember that here the electric field is going to be 0. And here your surface density is going to be the perpendicular vector of your electric displacement. Okay. So what I need to do then is to calculate the electric displacement. And I know that the electric displacement is just going to be epsilon times the electric field. So this is just going to be minus epsilon b naught rho a naught in the phi direction. And that's going to be d. Okay, and this is basically my rho s. Now, once I have the surface density, the surface charge density, then to calculate Q, is going to be the surface charge density times a differential area. For this particular case, I'm going to integrate from this edge to 1 meter and then to the bottom, and then the 5 meters. So I'm going to have Z is going to be from 0 to 5, and rho is going to be from, well, it's going to be these things. I'm going to call it from A to 1 meter. And the function is going to be this guy over here, minus epsilon d naught rho d naught, and then this is going to be dc d rho. Okay, this, well, I guess it's going to be rho dc. Okay, okay?
Yeah, I just got tickled in my throat.
This is killing me.
All right.
Okay, so the integral with respect of z is, because we don't have any dependency on that, that's just going to be 5. So that's going to be the depth of my plate. So here Q will be, notice that all this is constant. So I'm going to have minus epsilon v naught 5. And here I'm going to have the integral from a to 1 of 1 over rho of rho. Now, why this is not 0? Because this wedge doesn't go all the way to here. There's like this little section that we're missing. So that part that is missing, if this is 4 millimeters, that's my gap, and this is 45 degrees, then this is also going to be 4 millimeters. Yeah. So my limits of integration is going to be from A equals 4 millimeters to 1 meter. So I'm going to do Q minus Q naught 5, 4 to 1,000 of 1 over rho of the rho, and that's going to be minus epsilon v naught 5 natural logarithm of 1,000 over 4. Yeah. Notice that if we don't have, if these plates will be like a 1 meter and it will be in contact with the wedge, then we'll have a natural logarithm of 0, so that will be infinity. So we need to have that little segment of not touching. And once we have it, then I can replace some values. So I'm going to have here 1.5 times 8.854 times 10 to the minus 12. B naught is going to be the 50. Q is 45 degrees, so that's what, pi over 4. Times 5, natural logarithm of 1,000 over 4. And I don't have my calculator, so I'm gonna. Yeah, that's what they say. And double check my math, but I got like 23.34 times 10 to the minus 9 coulombs, or 23.34 nanocoulombs. Yeah, something like that. Yeah, that's the problem. We just needed to calculate Q. Now, if instead of having this dielectric, we had just air, then the only thing that changes is that instead of having this 1.5 factor, we will have just 1. But that's the only thing that changes.
So, could you get that electric from 1.5?
Oh. Teflon is like 2.3. Glass is 1.5. So could be a kind of glass.
No, it is glass.
Okay. Now, now we're gonna be doing a problem now that is gonna have dependency on 2 dimensions. So when you have these kind of problems, then the way you solve it is by using a technique that's called separation of variables. Okay, it's not nice. It's not pretty. This is gonna get nasty. So if you have you taken Fourier transformations? Have you learned Fourier transformations in any of your math classes? Fourier.
Weird. It sounds familiar, but
It's Fourier series. Fourier series.
Yeah.
Yeah. And differential equations.
Oh, I'm not.
You haven't taken that. You have taken that one?
I think the next question, but like that kind of stuff.
Yeah.
Okay, that sounds familiar.
Help or something like that.
Differential equations.
very familiar.
Okay.
But
So we're gonna be playing with those. It's gonna be nasty. Okay. So I'm gonna have a rectangular cavity in the X and Y plane. So it's gonna look like this. And this cavity is gonna have 4 walls. And I'm gonna have it like that. So these 3 walls, you can imagine they're connected, and these are going to be connected to ground. Okay, this one is connected to potential, to an electric potential. I'm going to say this is going to be 100 volts. Okay, this dimension is A, and this dimension is going to be B, and we can say that B is twice A. Okay, so first of all, what I'm going to do is I'm going to define my boundary conditions. So I'm going to look at what boundary conditions. So boundary conditions. So the first boundary condition is that the voltage when y equals 0 is going to be 0. So when y is 0, so when I'm here, is going to be 0, regardless of the value of x. So b of x comma 0, this is going to be 0. My second boundary condition is when x equals 0, regardless of the value of a, this is going to be 0. Well, technically, this is between a from 0 to a or 0 to b. But the third boundary condition is that when x equals b is going to be equal to 0. Finally, the last boundary condition is that when y equals a, this is going to be b naught. Okay. Now, in this case, we're working with 2 dimensions. So my Laplacian is going to look something like that. So it's going to have that the electric, the Laplacian of B, this is going to be dB, sorry. And this is going to be equal to 0. Okay, so this is the equation that we need to solve. We need to find an electric potential that satisfies this equation. Okay, now here's where the separation of variables come into place. I'm going to assume that my function v can be expressed as a multiplication of 2 functions. A function capital X that only depends on x, and a function y, capital Y, that only depends on y. I'm gonna rewrite this. So this will be my function v has dependency on x and y, but this is the product of 2 functions. Okay, so now I'm going to apply the Laplacian to this multiplication of functions. So I'm going to apply this here. Okay, so on the first term, I have double derivative of v with respect of x. So I'm going to have y And then on the second one, I'm going to have x divided by y. Now, this equation, I'm going to divide all these by b. Okay, so when I divide by b, then I'm going to have 1 over x plus 1 over y equals 0. Okay, now look at what this equation means. What this equation saying? Okay, I'm going to have a function x that only going to have x as a variable, and I'm going to derive this thing twice, and then I'm going to divide by a function x, and then I'm going to add it to this other function that only going to depend on y, and then when I add them together, it's going to be equals to 0. So the only way this can be true is if this is a constant and if this is a constant. Yeah, so this has to give you a number. This has to also have to give you a number. Otherwise, you won't be able to satisfy this condition. So this thing has to be to a constant, and this thing has to be another constant. Yeah. Not only that, but one is going to be negative, and one has to be positive, and actually the two of them has to be almost like the same. They have to be the same number. So if this is 5, this has to be -5. If this is -3, the other one has to be 3. Okay? Go ahead.
So we only have to solve one of them, and the other one, not only just the negative.
Oh, that's simple. So I'm going to make a choice. I'm going to say that C1 is going to be less than 0. That's going to be my negative constant. So I'm going to have minus C1 equals C2. And because they're actually the same constant, I'm going to call this thing K. Okay? So I can rewrite this equation, this one over here, and say 1 over x dx equals minus k, and 1 over y equals k. Yeah, or derivative of x dx squared equals minus xk. No, this is y. Okay. Now these are differential equations. If you have taken differential equations, these are very common differential equations. So I'm not going to derive it, but the solution of this differential equation with a negative constant here, this is going to be equals to a, what is the negative? A sine of kx plus b cosine of kx. And this guy over here with the positive constant, this is going to be C e to the kx plus d e to the negative k y ky. Okay, so this is my function x that only depends on x, and this is my function y that only depends on y. Okay, now remember the way we defined function v was basically the multiplication of those two functions. So now I can rewrite finally vx. Vx of y is going to be a sine of kx plus b cosine of kx ce ky plus d e minus ky.
Okay.
Okay, so I have an expression for V. Remember, that's what we want to find out. We want to find that electric potential, that expression that is find electric potential. But this electric potential has four variables, A, B, C, D, and we also have that K that we just assume a K, but we need to find an expression for that K. So we have five unknowns, okay? So yeah, that's what is not so easy to find. Now, what I'm gonna do is that I'm gonna apply the boundary conditions to this equation. Okay, so remember what was the first one? So we have the voltage is gonna be 0 when y equals to 0, right? Okay, so I'm gonna apply this. I'm gonna make y 0. So I'm gonna have e of x 0 I'm gonna have that. Okay, and from here I can say, okay, if I want this function to be 0, then t has to be equals to minus d. Yeah. The other function, now I'm going to do the same. I'm going to do the same with every single boundary condition. So the other boundary condition that we have, that's the floor. So when when x equals 0, this is going to be equal to 0. So this is going to be the left wall. So now x is going to be 0. So I'm going to have a sine of 0 plus b cosine of 0 times c ky minus c d minus ky. Okay, now that I can get rid of this variable d and I'm writing just in terms of c. Now, sine of 0, 0. So this is going to be 0. And this is going to be 1. Okay, so the only way this function can be 0 is if b equals 0. Okay, now I'm going to do the right wall. Now, the right wall, I know that, what is it? When x equals b, for all y's, this is going to be 0. So here I'm going to have a sine of kb plus c e ky minus c e ky is going to be equal to 0. Okay, so I'm going to make this 0. So this is going to be 0 when sine of kb equals 0. And that's going to happen when k times b be a multiple of pi. So from there, I can find an expression for k. K is going to be m pi over b, when m is going to be, can be basically any value. 1, 2, 3, etc. Okay. Now I'm going to rewrite what I have so far. So I'm going to have b of xy to be a sine of m pi over b x times c e ky minus c e minus ky. Okay, I'm going to factor out the c. Oops. Okay, and this over here, this e ky minus e to the minus ky, this is a trigonometric identity that I'm pretty sure you all remember. And this is going to be equals to AC sine of m pi bx plus sine hyperbolic of mpb over y. Oh, and there's a 2 over here. So eky minus e to the minus ky, this is 2 times this hyperbolic of ky. Yeah. Now, here's the tricky part. This m can have any value. So if I want to find an expression for b, I need to add all the possible values of m. So what will be this function when m equals 1 and 2 and 3 and 4 and so on? So I'm going to say b of xy is going to be equals to the summation from m equals 1 to infinity of cm sine of m pi bx sine hyperbolic of m pi by. Okay, so this cm is basically these two constants over here. Okay, we still have one more boundary condition. The last condition is going to be the top plate on that cavity. So in this case, B is going to be equals to B naught when Y equals A. So I'm going to evaluate this boundary condition in this very nasty function. So I'm going to have B naught equals to the summation Okay, so this is a Fourier series. Okay, and what I need to do is to find an expression for this constant. That's the last constant that I need to find out. Okay, now this is kind of like a trick, a trigonometric trick or an algebra trick. What I'm gonna do is I'm gonna use a function that's called orthogonality. And orthogonality basically says that, okay, if I have a function, if I have two functions and I integrate these two functions from A to B over a region, and this is equals to 0, then these functions are orthogonal to each other. Turns out that this happens to many of sine functions. So if you have a sine of nx times sine of nx from 0 to pi dx, this is going to be equal to 0. So sine is an orthogonal function to other sines with different factors. Yes. 0 to pi or minus pi to pi. And the only condition is that m has to be different than n. Okay, so I'm going to try to use this property to be able to solve for this constant over here. So what I'm going to do is that I'm going to multiply both sides by sine of n pi b x, and I'm going to integrate from 0 to b. Okay, so this equation over here is going to look like this. I don't have space. We're not even close. This will be a good moment to eat that chewing gum. Okay? You guys got it? Okay, I'll give you a couple of minutes.
Pretty sure that one.
Yeah?
Pretty sure that one.
I know.
We're here for a time. Who knows how long that'll be.
And believe it or not, this is the simplest way to solve these kind of problems.
So there should be three of these right there.
It's gonna be in spherical coordinates. It's gonna be kind of like a sun clock. Okay, so I'm gonna rewrite this equation. So one of the things with this equation, we integrate with respect of x. So that means that this sun hyperbolic is going to be basically a constant. So this can get out of the integral. Also, this Cm, this constant, can get out of the integral. They cannot get out of the summation, but they can get out of the integral. So I'm going to rewrite this. So that's you can finish from there. Okay. So here's the trick of all these methods. These functions are orthogonal. This integral is always going to be equal to 0, except when n equals n. So from all this infinite number of solutions, the only one that we care is when n equals n. Okay, so we only care when n equals care, and everything else is always going to be 0. Okay, so I'm going to have 0b Okay, and then this one starts getting a little bit more sense. Okay, so we still have a Cn over there, but this integral becomes doable, and this one is even more. So for example, I'm going to do the left side. So this will have BO cosine of n pi x over v, evaluated from 0 to b, and here we have what's b n pi. So this will be v naught b over n pi one minus cosine of n pi d of n pi.
Is that last part is n by b?
No, it's just n pi, no b.
Oh, yeah.
Okay, so that will be the left side. The right side, I'm going to have Cn sine hyperbolic of n pi a over b. That's just a constant, depends on n. This over here, this is just going to be b over 2. All that, this integral is going to be b over 2. So you have, let me see, sine square of n pi x b dx. This is 1/2 of b minus b sine of 2 pi x over 2 pi n, not 2 pi. 2 pi n x. So regardless of the value of n that you get, you're always going to get an even number. So all this is going to be 0, always. So at the end, you only end up with b over 2. Okay, so we have these two equations. So this one's going to be equal to this one. So I'm going to rewrite it here. Okay, so I'm going to have Cn sine hyperbolic of n pi a over b. That's going to be equal to 2 p naught over n pi 1 minus cosine of n pi. Okay, and this over here is going to depend whether n is even or odd. It's going to have very specific values. So this is n can only be integer values. So this is only going to have two possible solutions. So either it's going to be 4b naught n pi when n is even. No, when n is odd, or it's going to be 0 when n is even. Okay. Now remember, we still haven't found that constant. Okay. So, but now we can actually find the constant, this constant Cn. So Cn is going to be equals to 4d naught n pi sine hyperbolic of n pi a over b when n is odd. Yeah, so remember we have this function over here. And the only thing that we have done so far is to find DCM. DCM is this guy over here. So now we need to substitute this over here. And now we're finally going to get our function for the electric potential. I know.
The whole page of work for one variable.
Yeah. So V x of y is going to be 4 d naught over pi summation of n 1, 2, no 1, 3, 5 to infinity of sine of n pi x over b sine hyperbolic of n pi x over b over n sine h and that's it. That's it. That's your Vx. That's your function for electric potential. Once you have that, you can calculate the electric field, you can calculate the electric displacement, and you can calculate current, everything. Now, how does that function looks like? Like, how would you even make sense of that? So, you don't.
I'm gonna show this like perspective physics students and be like, we don't do this in 3 years and it's gonna make sense.
And then you'll drop our physics department. Like, I like talking about some of the stuff my younger brother's in like high school physics. He's like, wait, what? Come again?
I show my roommates who are accounting, NMS, and psychology majors, and they are like,
These problems that make you feel like strong, like, holy crap, yeah, I can do this.
No. Like, I understand more or less what's going on. Even I'm just like, oh.
Okay.
Like, I'll imagine somebody who has no idea what's going on seeing something like this.
It will start making sense. It's just, I mean, it's the first time you see it, so it's always like, it's a little bit overwhelming, but it will start making sense. Okay, so this is just a small code. It's in the back of your book, or it's on at the end of the chapter. And this is basically calculating those sine and hyperbolic sine functions. So this is
It's really important.
sine of n pi times x over b. This is sine hyperbolic n pi times y over b. And these are the denominator. So these, oops, is this equation over here. Okay, this is, I think this is y. Yeah, that's y.
Imagine you make it all that way, and like, go down or something, just to miss that.
So that's basically that function. Here, just some counters it divides the rectangle, all the cavity in the little pieces, and it just calculates the electric potential at each point. And here's the summation. Okay, so it shows you that graph, and it kind of makes no sense, this graph, like why are we seeing this graph? So I'm gonna rotate this graph.
I like this view better.
Okay, so what you're seeing is the electric potential, and you're seeing how the electric potential is changing inside that cavity. So the top, what the fuck? So if you see your graph, if you see the plate, your cavity, sorry, we saw that this one is going to be a B naught, and all these are going to be in ground. So, you know what? Let me redraw this. I'm going to put a little bit of high resolution. There you go. Yeah. So when you get closer to the top, you get your B plus, your B naught. This is to be going to be very close to that 100 volts. And as the electric field moves away, and you're moving away from that electric potential, then and you get closer to the other walls, well, the condition is that the electric potential here has to be zero. So as you get closer, you're going to see how you get very close to this zero value. So this will be the electric potential in that space. Once you find an expression for the electric field, you could do something similar for the electric field. You will be able to graph it. So I don't know, I thought it was kind of cool. Yeah, so embrace it. This is like a actually pretty cool application of calculus and math and physics and all this stuff. We'll do. I'll show you a couple more problems involving this on Friday, so it gets a little bit more familiar. But as you can see, like it was just one problem, and it took us the whole hour. So
That's what I was saying. Really, we're going to do 2 of these on Friday?
oh well, I don't know, maybe just another one. But yeah, brag about it. This is physics at its core.
I don't think anyone's going to care about us bragging about this. Going to be like, well, thank God I'm not doing that.
I'm gonna slap this down in front of all my roommates and say, figure this out.
I'm not letting you do it until you give me the